Hi everyone. In the last class we were discussing about the unsteady state heat transfer. I just gave you an introduction about the unsteady state heat transfer. Okay. In that introduction we talked about lumped capacitance method. Okay. Now let us see, that was the first method that we were talking about. So let us see what this lumped capacitance method is. Okay. So if I bring an example, we consider, in this case we consider the internal resistance to be negligible, internal resistance in a solid to be negligible. Okay, so if I bring in an example, let us say we are talking about a condition where let us say we are talking about a condition wherein we have some liquid in a tumbler. Okay, now let us assume that the temperature of that liquid is ambient temperature, or maybe T infinity. Okay, now all of a sudden we are dropping a ball, a steel ball or something, which is at a temperature Ti into it. Okay, so here in this case what we are considering is the temperature profile inside, or the temperature gradient inside the steel ball is not present, which means that at every point in the ball, the temperature is Ti. At every point in the ball the temperature is Ti. Wherever you take, the temperature is Ti. So there is no change in temperature with respect to space. So there is no temperature gradient. Okay, so that is the basic idea behind the lumped capacitance method. Okay, now let us see if this is the condition. Then if this is the condition, at T is equal to T less than 0. Okay, that is at time equal to 0 or lesser than that, then that's at the starting position. At the starting position, if the temperature is Ti, and let us assume that the temperature changes with respect to time, that is T is a function of T. Okay, the capital T, which stands for temperature, is a function of the small letter t, which is time. Okay, that is for at a time greater than or equal to 0. Okay, so initial temperature was Ti, and then the temperature goes on increasing or decreasing, or goes on changing with respect to when the time changes. Okay, with respect to the time. Okay, so one very important thing that we have to consider here is that the energy equation, or the heat equation. Now the heat equation was d square T over dx square, or the three-dimensional heat equation was d square T over dx square plus d square T over dy square plus d square T over dz square plus, if you're considering the heat generation term, this is q dot over k will be equal to 1 by alpha dt over dt. I'm using the small letter t for time. Okay, in some books you can find tau also for that, but here I'm using the small letter t for time. And one thing that I have to say is that all the figures that I have taken is from the textbook Fundamentals of Heat and Mass Transfer from Incorpora. Okay, now so in this case, when the temperature gradient, when there is no internal change in temperature, or if the temperature inside this ball is same, we don't have a spatial change in temperature, which means that there is no change in temperature with respect to the x direction. Okay, if this is the ball, once again in the x direction, if you take, there is no temperature change, so this at this position is Ti, and this position is also Ti, so this term will go to 0. Okay, similarly if you take the y direction and the z direction, you have the same thing. So there is no spatial change, means all these terms will go to 0. Okay, and then let us assume that there is no internal heat generation, which means that this also goes to 0. Then what remains is only this thing. Okay, but we know that it is unsteady state, there is a change of temperature with respect to time, which means that this cannot be equal to 0. So since all the other terms are going to 0, but this is not equal to 0, this term is not equal to 0, since it is an unsteady state, we know that this term is not equal to 0. Okay, so since this is not equal to 0, the energy equation as such cannot be considered. So in this case, in this condition, what we do is we just take the conservation of energy. Okay, conservation of energy, that is minus of E out, and let us assume that the energy that is going out is taken as negative. The rate of energy that is going out will be equal to the energy that is coming in. Okay, let us assume that the energy that is there inside is equal to the energy, that is rate of energy going out. Okay, so if you are consider now here the internal, the temperature is Ti here, and we know that Ti is greater than T infinity, where T infinity is the temperature of the ambient temperature or the temperature of the liquid. Okay, so at any time Ti, where until this Ti becomes equal to T infinity, until that time there will be a change in temperature. Temperature goes on decreasing, which means that there will be a heat transfer from inside this to the outside surroundings. Okay, there will definitely be a heat transfer from inside this to the outside surroundings. Now as you know that in the figure the surroundings was liquid, right? We have seen that the surroundings was liquid. Now since it is liquid or any fluid, the prominent mode of heat transfer to the this thing from the solid is actually convection. Okay, so there is convection from here to here. Okay, and there is conduction here. The prominent mode is conduction. Okay, but we know that we here in the lump capacitance method we have considered that the temperature gradient is 0. So the temperature gradient is 0 means in the Fourier law we have seen that Fourier law is minus q, or q is equal to negative Ka dt over dx, right? Fourier law we have seen that this is the dt over dx, which means that, or if you neglect A, then the heat flux will be equal to q will be equal to, sorry there is no negative there on the other side. Okay, we'll remove the negative. So q will be equal to minus k dt over dx, right? So in the absence of the temperature gradient, let us see what happens. So q over dt over dx equal to k, negative k. Now if dt over dx, which is the temperature gradient, is equal to 0, then k tends to infinity. Okay, which means that you will have infinite thermal conductivity, which is not a possible case, which is actually impossible, but then we can just make an assumption of that sort, that is this is equal to infinity, k tends to infinity. If dt over dx is equal to 0, then k tends to infinity. We can assume that, we can just make an assumption of that sort. Okay, that is what we are doing here. K tends to infinity. When k tends to infinity means when the thermal conductivity k tends to infinity, means the thermal resistance, that is L by Ka, tends to 0. Okay, because resistance is actually L by Ka. Okay, when k tends to infinity, this tends to 0, which means that the thermal resistance is almost 0. The conductive resistance is almost 0, which means in turn gives us that the temperature gradient is almost 0. Okay, so usually if we have a block of like a slab or something like that, we take it like this, right? The temperature gradient is given like that, but when the which means that the temperature at this position is T1 and this position is T2, where T2 is less than T1, but here we consider T1 is equal to T2, which means that the temperature gradient, the thermal conductivity Q conduction from inside this, you will have a straight line like that, T1 and T2. Okay, so we consider this complete thing as a single lump, and we assume that there is no resistance inside this, and then there is only convection from this towards outside. Okay, so under these conditions we can write that the heat convected to the surroundings. So heat convection equation is given by So if you write AS as a surface area, heat convection equation is given by T minus T infinity, where T is the temperature at any particular time small letter t. Okay, and T infinity is the ambient temperature. So this will be equal to rho Vc dt over dt. Okay, that is the rate. This is in the rate form. This rho Vc is actually mc. Rho Vc is mass times S. So this is mc delta T with respect to time. So or per unit time. So we can write it as rho Vc dt by dt. Okay. So this is the main condition for unsteady state heat transfer when we have the when we assume the lumped capacitance method. Okay. So minus HA times T minus T infinity will be equal to rho Vc times dt over dt. Okay. Now let us define a variable theta, that's a temperature, as T minus T infinity. Okay, let us define this. Theta is defined as T minus T infinity. So when theta is defined as the T minus T infinity, what do we have? D theta will be equal to dt over dt. Okay, d theta over dt. Okay, d theta over dt will be equal to dt over dt. Fine. Then we can write that. Then we can write this equation as minus HAS times theta will be equal to rho Vc, rho C is not subscript, it is this thing. Okay, C is that rho Vc times d theta over dt. Okay, now here we have only changes with respect to time. That is the reason why I have taken the total differential rather than, or ordinary differential equation rather than the partial differential equation. Okay, so this is HA theta will be equal to rho Vc d theta over dt, and from this I can write negative of dt will be equal to rho Vc, C is capital this thing, dt over d theta over HAS theta. Okay, so I can write it like that. And now let us say we are going to integrate this to find out what is the temperature distribution. Okay, so if I integrate that, we can get negative of integral 0 to t. So we're taking from any time, from 0 to any time t. So 0 to t dt will be equal to rho Vc. All these things are constant for a particular fluid and particular substance. So rho Vc, and for H is equal to also a constant, so that will be from theta I. We know that at time t equal to 0, the initial value of theta is theta I, and then let us say it is theta at this point, so this is d theta over theta. Okay, now if you integrate that, you get now if you integrate that, so here actually theta I will be equal to Ti minus T infinity. Okay, Ti minus T infinity, which is the temperature corresponding to the time t equal to 0, small letter t equal to 0. Okay, Ti is equal to t of 0, that is when t equal to 0. Okay, so that is why it is t of 0. Now we have if you integrate this, you get, so minus of t times 0 to t will be equal to rho Vc over HAS, which is the surface temperature, will be equal to ln theta times theta I to theta. Okay, from that we get if you apply the limits, you get, which gives us T will be equal to rho Vc over HAS, where AS is the surface temperature. Okay, ln theta I over theta. Okay, if you go on with that, you get theta I over theta, or theta over theta I. Theta I will be equal to, because there's a negative sign there, so I'm taking theta over theta I will be equal to e raised to minus AS over rho VC times T. Okay, so this is the equation for the temperature distribution, that is theta over theta I will be equal to e raised to minus HA over rho Vc times T. Okay, now this rho Vc, the quantity, this quantity rho Vc time rho Vc over HA, yes, this is having the dimension of time, and that is called as the thermal time constant. So this is the thermal time constant given by tau Th. Okay, this is called as, this quantity is called as the thermal time constant. So this can be written as, this is equal to e raised to minus 1 over tau Th times T. Okay, we'll come to that later on. We have the reason why we call it as a thermal time constant. We have some reasons for that, and we'll see what is the behavior of all these things, the temperature gradient, what happens to the temperature gradient when the time constant changes. We'll see with the help of a graph. Okay, so if I just import that thing, if I just bring in that picture, we can see that, okay, from this figure, if you look at this figure, okay, once again this figure is taken from Fundamentals of Heat and Mass Transfer in Cropra 7th edition. Okay, courtesy to that book. So you can see on the left side theta over theta I is given, that ratio is given there, and to the right side T is given. Okay, so if we look at each picture, if you look at each graph, you can see that as the value delta tau T, which is the time constant, okay, thermal time constant, increases, that is, this is 1, this is 2, this is 3, this is 4, as the time constant increases, we can see that it takes more time for the curve to come to equilibrium. That is theta, here we can see that theta over theta I is 1, so later on theta over theta I is 0. Okay, or very close to 0, which means that they are unequal. Theta is approximately equal to theta I. Now we know that the theta is actually the final value of the temperature, and theta I is the initial value, temperature difference. Okay, so when temperature difference T over T infinity is 0, finally it becomes in equilibrium. So we can see that when the value of tau T increases, it takes more time. It takes more time for this to come in equilibrium. Now this can be written as rho Vc is defined as two terms, will be equal to, this can be split into two terms, that is, this is equal to 1 over HAS times rho Vc. Okay, and this term is called as the resistance for convection, because the term is 1 over H, so this is resistance to convection, and this term is called as the thermal capacity. Okay, thermal capacity. Okay, so this can be written as RT times CT. So if you look at the figure, you can see if the R increases, still the value of tau increases. When the R increases, the value of tau increases, which means that when H should decrease, right? When H decreases, R increases, the resistance increases. Or if R increases, then it takes more time for coming into equilibrium. That is clear, right? If the value of H decreases, if the value of the thermal capacity or convective heat transfer coefficient decreases, then the amount of heat transferred will be lesser. It takes more time to for the heat to get transferred, then it takes more time to come into equilibrium. Similarly, the thermal capacity, when the thermal capacity increases, means it will take more time to come into equilibrium, right? Because when the thermal capacity increases, it takes more time for the object to give away heat. Like you can see in the case of water, the thermal capacity is very high for water. That is the reason why water gives away heat very slowly. like if you see in the early morning, like if you heat water and then you leave it for some time, and along with water, so first of all if I heat water and then leave it for some time, along with that I heat some other metal or something, metal block, to the same temperature, and the first one, and after say some time t equal to 20 minutes or something, if I look at the temperature of this metal block, so this is the metal block, initially the temperature of the metal block was Ti. Let us assume that the initial temperature of this is also Ti. Okay, now initial temperature both is Ti. Let us say T20 of the block, so TIB and Ti water. Initial Ti water is equal to Ti of the metal block. Okay, now T20 of water, 20 minutes, that's 20 of water, I meant 20 stands for 20 minutes. Okay, now we can see that T20 of water is greater than T20 of the block. The reason is that the water is having higher thermal capacity. This is an experiment that we have already done in the class, so I hope you you remember that. If you can recall the experiment where we heated a metal block and then we actually exposed it to the atmosphere along with heating water to 100 degrees Celsius, we actually heated a metal block also and then allowed both to cool down, and we found out that the metal block actually cools faster. The reason was that the thermal capacity of this water is higher. So you can see, if you go back to the equation, if you go back to this equation, we can see that when the thermal capacity increases, the tendency of the object to give away heat reduces, and when the H increases, the resistance actually decreases, and when H decreases, the resistance increases. So when resistance increases, it takes more time for the object to come into thermal equilibrium with the surroundings. Okay, that is what this figure says. Now we can write this HACS over rho Vc times T. We can just split it into some, we are actually trying to bring it into some this thing non-dimensional form. I'm splitting it like that. So this times AS square, I've brought the AS to the denominator, K over rho Vc square, so V square C times T. Okay, now the first term can be written as, the first term, if I take that, V over A is L, so this can be written as HL over K, where this L, let us write it as C, LC, which is the characteristic length. We'll discuss about the characteristic length in the next class. And rho Vc over K, okay, we have rho Vc, right? So rho Vc over K will, so if you take A square over V square, and if I remove that V, okay, V to the other one, I'll get it as K by rho C is actually, this can be split it like this, okay, into three terms. This can be written as 1 over L square, and K by rho C is actually alpha and T is the time, so we can write this as alpha times T over L square. Okay, now this number, this is a non-dimensional number, so that is Bi, that is called as the Biot number. We will see the physical significance of the Biot number, and this is the Fourier number Fo. So using these two, we can write theta over theta I is equal to e raised to minus Bi times Fo. Okay, so here what we have done is we have derived an equation for the thermal or the temperature distribution. Now after that, in the next class, we will actually find out, what can I say, what is the heat flux. Okay, so until then, okay, so see you later.